Okay, so today I want to talk about secure quantum computing. And I should say a little bit about what I'm going to talk about first. I'm basically going to go through the developments that have happened, say, over the last 7 or 8 years in this area, and they've been picking up pace recently. There's now, at this stage, really quite a large literature on the area. And so I want to tell you a little bit about where this has come from and some of the more recent results and kind of where it's going. And in order to do this, I'm going to restrict to two particular types of secure computation protocols. Basically, I'm going to be talking about delegated quantum computation. So the idea of delegated quantum computation is that, at least as it was originally envisaged, when people were imagining what the future would be like, we thought, oh, well, maybe there will be, maybe it will be, well, we know it's hard to build quantum computers, so maybe they won't be widely available. So maybe when quantum computers first appear, they will be, kind of hooked up, you access them over the internet, something like that, but really they're sitting in some facility in a university or in a company somewhere. And it turns out that this is a prediction that's starting to become true. So this is a screen capture of the IBM quantum experience. So this is basically a 5-qubit, 5 superconducting qubits that are hooked up to the internet. And there's a little interface on it, so you can build your quantum circuit. And you can hit run. And when you run it, it runs the circuit that you built on this device sitting in IBM in the US. And you get the result back sometime later. So actually, it seems like good timing to talk about this, because just as I was going to bed last night, I noticed on Twitter that IBM had unveiled a 17-qubit device that they are also planning to hook up to the internet. So it seems like this model where you have a computer sitting at some center somewhere, but you have maybe many users trying to access it, maybe remotely or at least from terminals in the same region, is not that crazy. So it seems like it's starting to be the model that people are pursuing, at least for kind of devices in the medium term. Okay, so the first type of protocol I want to talk about is something called blind quantum computing. So the basic idea in blind quantum computing is that you have some user, Alice, and you have some guy who is operating a quantum computer called Bob. Or, this doesn't have to be one person, but you can just think about it as the quantum computer side of the protocol. And the basic idea is that Alice has limited computational power. So basically, she has a laptop or something like this, or she has a desktop or whatever, and she would like to communicate with Bob with this remote quantum computer in order to be able to run a quantum computation. Now, the important thing about this is that Alice doesn't have enough power to be able to perform the computation herself, and she also doesn't trust Bob. On Bob's side, he has the quantum computer, so he can run the computation, and he's willing to help Alice do it. Maybe she's paying him. But he won't give Alice the device. So maybe that's because it needs to be in some centralized facility. Maybe it's because the device itself is sensitive. Maybe because it's hard to calibrate, or maybe just because there's commercial, there's trade secrets or something involved, or anything like this. And so Bob doesn't want to sell a device to Alice. Then she could run the computation on her own premises, completely isolated from the rest of the world. Try to build some chamber that doesn't let any signals in or out, and use it to run her computation. But in this scenario, she can't do that. So she has to rely on Bob for help. So what we would like is for some way for Alice to delegate the computation to Bob that doesn't reveal what the computation is to Bob. So she's trying to keep the computation to be performed secret from Bob. So even if someone has complete access to the hardware running the program, they shouldn't be able to learn what the computation was. So there's kind of an appeal for this kind of thing because if you think, for example, a lot of computation is currently delegated, just classical computation is run on, for example, Amazon, on the various Amazon cloud offerings. So this is something that happens a lot in the classical world, and you could guess maybe it's likely to happen in the quantum world given recent developments. So the first thing I want to talk about is what it means for something to be secure in this model. And I would like to say that all of this work was done right at the start when people started looking into these protocols, but it wasn't. It came much later. So the original idea behind hiding a computation, or this kind of blind quantum computation, is that Bob shouldn't be able to learn from the information he receives during the protocol what Alice's computation was. So if you try to formulate that in a relatively direct way, you come up with something like this. A protocol P is on input X is blind while leaking at most some function L of X if the distribution of classical and quantum information obtained in the protocol P is fixed and dependent only on the leaked information L of X. So you could say, why do we have this leaked information at all? And one of the reasons for this is that when Bob runs a computation, he is going to know something about the computation. That's inevitable. Unless he doesn't know when the computation stops, he's always going to learn some upper bound on the amount of time he spent running the computation. So he'll learn something about the complexity of the computation. And this is basically going to be the circuit depth, or at least an upper bound on the circuit depth, because you could always pad it. So you could always do operations that cancel out after a certain time to make it appear longer than it really is. The other thing is he's going to know how much memory his device used. If he has 17 qubits in his device, or 100,000 qubits, or whatever, he knows he didn't run something with 28 million qubits, because they just can't all fit in his device. So inevitably, he's going to learn something about the number of qubits involved in the computation and the depth of the computation. But you would like him to learn no more than this. Okay, and what we're saying basically is that if you know the number of qubits he uses and the amount of time he uses, then all of the information in the protocol that's exchanged from Alice to Bob, and vice versa, should be independent of the computation Alice is running. So from Bob's point of view, the communication should look identical, independent of what Alice's computation is. Okay, so it turns out that that's a reasonable enough definition, but it's not very well behaved if we think about composing various protocols together. So if we want to use blind quantum computation as part of a larger protocol. So for example, there have been some proposals to use blind computation as a mechanism within quantum money protocols to verify that quantum coins are valid or not. Now, a problem with this is that the security of most of the protocols that I'm going to discuss is only proven as a standalone protocol. If Alice has some additional information, if Bob has some additional information about what Alice might be trying to do, or has some way to influence the distribution of her possible choices of computation, then in that case, the security proofs don't really cover it. So what we need is a stronger form of security. So we need a stronger definition of security. And to that end, there have been introduced various composable security definitions. And by that, what I mean is that they specify the protocol. They specify blind computation as some kind of ideal protocol. So in this case, the left side is taken to be Alice's input and output. So Alice specifies some input state psi A that contains a description of the computation to be performed, including where any measurements are and any initial state that needs to be included. And she's going to get out the output of the computation as row A. And then on Bob's side, he can essentially enter a single bit to decide whether he's going to cheat or not. So he's going to make a decision as to whether he completely complies with the protocol or whether he wishes to deviate in some way. And when Bob decides to cheat, this bit is essentially set from 0 instead to 1. And when Bob decides to cheat, some leaked information comes out, L of psi A, that's essentially this, the equivalent of this Lx up here. So it's just leaking something about the input state psi A. And then Bob also maybe gets to inject some description of a way of cheating, a way of disrupting the protocol. So what this B captures here is basically Bob's choice of how to disrupt the computation. Okay, so the only thing that Bob is learning is whatever the leaked information is, but he has some ability to perhaps affect the outcome of the computation in some predefined way. Okay, so this gives a very kind of idealized picture of blind quantum computation. And what you would like to be able to do is say, if you can achieve this, it doesn't matter how you achieve it. Once we know that a protocol satisfies the security, this kind of composable security definition, then what we can say is that, well, wherever we actually have a real protocol, we can just erase it and just draw in this ideal box instead, because we know we've hopefully proven that the protocol we're going to use is equivalent to this ideal formulation here. So in this framework, you have a client. So if we actually look at a real protocol, you have some client and you have some server, and the client implements some protocol on their side. So they have some set of instructions that they have to follow, which is called, we'll label it pi A. And on the server side, there's some set of instructions that they follow, which we can label pi B. Now, the server may be honest or they may be dishonest. So we don't really know what pi B will be, but we know what pi A is, because Alice isn't going to try to undermine her own computation. We only need to worry about the server deviating from the protocol. So the basic idea is that when we combine Alice's protocol with Bob's protocol, interacting via some communication channel, maybe with multiple rounds of Alice sending something to Bob and back and forth, maybe quantum information, maybe it's classical information. What we would like is we would like to say that this here is basically equivalent to our ideal functionality. And in order to do that, we need to set up some definition that we need to prove our protocol satisfies. So we need to say the protocol is blind if it satisfies some particular mathematical property. And we want to capture the fact that pi B might change. So if Bob is acting maliciously, he might change what pi B is. So what we do is we get our security definition from combining this ideal functionality with some simulator here. And what this simulator does is it has the same connections as Bob's side of the ideal functionality. So where the ideal functionality has an input of some bit from Bob deciding if he's going to cheat or not, the simulator has an output that gives that bit. And where it leaks some information, L of psi A, well, there's an input on the simulator for that. And where there's some B, that's some CPTP map that's injected to disrupt the computation, well, the simulator has some output for that. So that tells us what the left side of the simulator is. So I guess you can see we could plug this simulator. The left side of this simulator plugs into the right side of this ideal resource. Okay? And on the right side of the simulator, what you have is you have this kind of back and forth communication that matches up with Alice's side, with the side of protocol pi A that interacts with the communication channel. So it's basically, the simulator basically plugs into the ideal resource and then generates the same communication stream, the same kind of interaction with the server as would happen if Alice was running her protocol pi A. Okay, so the basic idea then is you say that a protocol is blind if the protocol, the bit in green here, this client with pi A and her input psi A and her output rho A if this piece and the communications channel is equivalent to plugging the simulator directly into the ideal resource. Now, you could say, why is that blind? Well, the reason that's a good definition for blindness is that if you look at how the simulator connects to the ideal resource, only the leaked information passes between the two of them. Only the information L psi A that is allowed to be leaked in the definition of blindness is passed from one to the other. There's no way when you plug the simulator into the ideal resource that anything about psi A other than L of psi A can be passed to this interface on the far right-hand side. Okay, so that gives a much stronger definition of blindness than this kind of simple definition that we just expect the distribution of information to not depend on the input. But as I say, this is much later work. But it gives a very concrete definition for security definition. Sorry, a very concrete security definition for the problem. So, okay, so essentially the first protocol that could be called blind quantum computation was introduced by Andrew Childs in 2005. And he called it something different. The term blind quantum computation wasn't coined until some time later. Essentially, he proposed this under the name of secure assisted quantum computation. And the basic idea was that you have some client who has a large quantum memory. So they can store a lot of qubits. And they're able to perform Pauli operations on those qubits. So they have big memory, they can perform Pauli operations on them, and they can send them to and from a server. And what the server does, the server is basically a universal quantum computer, and the basic idea is that the client will send qubits to the server, and the server will apply some gates on them, and they'll be returned to the client. Now, you could say, well, if the client has this capability here, the ability to do Pauli operations on a quantum memory, can they not do everything? And the answer is not really. They don't have access to entangling gates. They don't have access to things like Hadamard's. So if they start out with a whole bunch of qubits in the 0 state, they can only swap them to they can only flip them to the 1 state. They can't get a plus state out of it, for example, and they certainly can't make bell pairs. So there's a limited amount they can do. And if they have access to a server that can perform just individual Hadamard gates, individual C0 gates, individual T gates, for example, just on a single qubit or 2 qubits that are sent to them and then sent back, then they can perform a universal computation. And the basic idea of how you hide the computation from the server is very simple. So you start out with some initial state for your quantum computation, and then you use the random Pauli operators you're allowed to apply a quantum one-time pad to the qubits. And then you send the qubits to the server, and the server applies some gates. They just apply some fixed sequence of gates. They're always going to apply a Hadamard, then a C0, then a T, or something like this. And they'll just go through that cycle again and again and again and again. And when you want to perform a C0 on your computation, you send a qubit that's part of the computation. And when you want to just ignore a gate, you know the server is going to perform maybe a T gate, but you want a C0 gate. So what you do is you just send them some extra qubit. You don't need to use the qubit you don't need to use a qubit in your computation. You just use a spare one you have as a dummy. And you send that to them. They waste the time of doing the T gate and they send it back to you, but now you're on to the next gate in the sequence. And you can do that to choose which gates you want at any time. So all that's happening is you're choosing which qubit to send at any one point in time. And then when you choose the qubits to send, you apply a new quantum one-time pad every time. And you could say, well, isn't this quantum one-time pad going to interfere with the computation? And the answer is not really. So the quantum one-time pad won't commute with all of the gates. So it's not like you can do the whole computation with a quantum one-time pad on your data. But you can correct for its effect on each gate with another gate. So if the first operation I want to perform is a Hadamard gate, I can account for the effect of the Pauli operation when I send it to the quantum computer. And when I get it back, I know there's just some different Pauli correction I need to apply in order to obtain the true state. I can do the same with any Clifford group gate. So I essentially get the whole of the Clifford group for free because I know what operations Bob's going to apply. So I can always correct for its effect on the one-time pad. The only time you start to run into difficulty with this is when you have something like a T-gate, when you have something outside the Clifford group, or a Toffoli gate. And when that happens, you know you're going to need to perform some correction. However, if it's a T-gate or if it's a Toffoli gate, you know the correction you're going to perform is inside the Clifford group. So either you have to perform some correction, like a C0 gate for a Toffoli gate, or not, depending on the particular key you chose. But you know that yourself. The client knows what correction they need to perform, so they're just adapting the circuit to their key to compensate for the effect of the quantum one-time pad as it goes through the gates of the circuit. And this lets a client delegate a computation to a server in privacy, essentially perfectly private. The main drawback of this is that the client needs quite a lot of resources. They need a large quantum memory, and they need the ability to perform high-quality Pauli operations, so they're not polluting the computation with noise. And they need the ability to be able to choose qubits arbitrarily from within their memory, apply the Pauli operation to them, and then transmit them, and also receive them back from the server. So while this is not enough for universal computation, it's still quite a high load to place on the client. So that brings us to a big class of protocols for blind computation that have been proposed. The basic idea behind all of these, they're based on a model of computation called measurement-based quantum computation, which was initially proposed by Reisendorf and Briegel. And the basic idea is that you prepare some entangled state for your computation, and you have some control computer that decides how you should measure this state. So there's some big entangled state that's prepared. The first qubit gets measured in some basis, and then based on the output result, the measurement basis for the next qubit is decided, and so on. Now, generally in measurement-based computation, the resource state that's prepared is not dependent on the unitary you want to implement. So it doesn't depend on the computation, except maybe on the depth of the circuit you want to implement and the width, the total number of qubits. So the way this is used in blind computation is generally fairly straightforward. Generally what's done is that you have some client who's taking over the part of the control computer, and you have the server, Bob, who's taking over the preparation of the resource state and maybe some of the operations involved in measurements, something like that. Okay. Now, there's a number of different protocols, and they work in different ways. The basic idea behind measurement-based computation is that you have some set of input qubits that will propagate through the quantum state. So they're usually in the early work on this, they're always kind of starting from the left-hand side of the resource state and propagating to the right-hand side. But you can make some other resource states that are that it's less clear how they propagate through. But generally, you're going to be able to think of some input set of qubits that are measured essentially first, and when they're measured, the information contained on them is propagated to the next layer of qubits along some particular lines that I'm going to call lines of flow. Basically, each of the qubits in this state, each of the vertices in this graph represents a physical qubit prepared in a plus state, so an equal superposition of 0 and 1. And each of the edges in the graph, including the ones with arrows, correspond to a CZ gate, so a controlled phase gate applied between those qubits. So by making adaptive measurements, you can propagate the information from the input qubits over to the output qubits while applying some arbitrary quantum computation. And the computation that's performed depends only on the measurement angle and where the particular edges in the graph are. Now, it turns out that you can pick certain states or certain families of states, like this kind of rectangular arrangement here, where just the black qubits, the black lines represent the edges and the black dots represent the vertices in the graph, that are universal. So this is just some rectangular, some kind of rectangular arrangement, and it has a standard pattern to it. So there's only two parameters that specify this family, basically how long it extends and how far down it goes. But it gives you just some rectangular graph. And the basic idea is that the depth down this direction represents the total number of logical qubits in the computation, and the breadth in this direction represents the depth of the quantum circuit, so the total number of gates that are going to be applied. So the longer this is, the more sequential gates can be applied. And the further down it extends here, the more logical qubits can propagate through it. And essentially, you can think of the qubits as propagating from left to right along straight lines. And it's possible to break this up into these regions of 10 qubits each and specify angles on them to measure in the xy plane. So these are all measured in the xy plane. And depending on how the angles are specified, you can either use this to implement arbitrary local rotations on either of the two logical qubits that passes through one of these cells, or to apply an entangling gate, such as a C0, between logical qubits. So this gives you a resource state that's universal for quantum computation, but particularly it's universal with just xy plane measurements. So the first protocol to exploit this was, well, so I'm involved in it, but also Anne Broadbent and Elham Keshefi came up with this. And the basic idea is that the client is just going to prepare some single qubit state and send it to the server. And the server is going to entangle these single qubit states to make one of these brickwork states. So the same kind of universal state, I mentioned on the previous slide. Now, the difference is, rather than preparing plus states, Alice is first going to apply some random z rotation to the plus state. So now it's not necessarily a plus state, it's just some random state in the equatorial plane of the block sphere. And she sends it to the server. And the server arranges these in some regular grid, and then applies these control phase operations between them to generate this massive entangled state. And you could say, well, that's not the resource state you told us about, because these weren't plus states. But they had this random z rotation applied. And this z rotation z rotation commutes with the controlled phase gate. So it's the same as if we prepared the ideal ideal brickwork state here. So as if the server had constructed the ideal state, and then Alice had applied these random z rotations after that state had been prepared. And then this is just because her z rotations commute with the control phase operations. So this gives her a way to perform measurement-based computation, where Alice is sending a measurement angle to the server. They're saying, now rotate this qubit by pi over 4, something like that, and measure it in the x basis. So Bob is supposed to do a z rotation by, say, pi over 4 on a particular qubit, and then measure it in the x basis. But that pi over 4 adds on to the random rotation that Alice previously applied. So in this way, she's hiding the true rotation, the true measurement basis from Bob. And it turns out that this is sufficient to hide the entire computation. You can kind of work through it and see how it works. Essentially, Alice is preparing some randomly rotated states in the equatorial plane that we can write as a true plus state, plus some random rotation, plus some random phase flip. And she's sending them to Bob. He's performing some rotation and then measuring in the x basis and sending the result to Alice. And essentially, it turns out that all of these operations cancel, so that essentially Alice can figure out the true measurement result, which is M1 here, that would have happened had Bob measured his qubit in some basis phi1, even though he's not measuring in that basis, right? It's just everything cancels out. All of the random rotations that are applied in the initial preparation get cancelled out by compensation for it in the measurement in the measurement basis that Bob is told to measure on. So that Z rotation he's told cancels out the randomized effect for the initial rotation and then implements the correct rotation. So Bob is sending Alice essentially the correct outcome for the computation. The main difference is that this random phase flip here means there's some random bit flip applied to his outcome. So actually it's encrypted with a one-time pad. The information he's getting back has had the information he's sending Alice from the measurement results essentially has random phase flips built into it. And I'm not going to go through it. I'm not going to go through the proof. But it turns out you can prove not only that this gives you the right computation, but that the distribution of information he obtains from these qubits and from the classical angles is always maximally random. So essentially, the random phase flip has the effect of ensuring that no matter what qubit he sends to Bob, Alice sends to Bob, Bob will always perceive it to be the maximally mixed state, independent of everything else he receives in the protocol. So that qubit will always look completely random. Also, the measurement angle, he's told, will also be uniformly random out of the set of possible angles he could be asked for. So this satisfies the first definition of blindness, and with much more work, it also satisfies the second, stronger composable security definition I mentioned, but it's really non-trivial to show that. The other thing you can do is you can hide not just XY plane measurements, but you're also able to hide Z basis measurements. And the way that's done is basically by noting that a measurement of a qubit in the Z basis commutes with these control phase gates that are applied by Bob. So really, you could make the measurement before you ever send the qubit to Bob. So what happens if you measure a plus state in the if you measure a plus state in the Z basis? Well, then the result is you're just going to be randomly sending Bob a 0 state or a 1 state. So this gives you a way of hiding XY plane measurements and Z measurements. It's fairly involved, and it's fairly involved, but it seems like it doesn't have very much overhead. Alice only needs to be able to prepare single qubit states and transmit them to Bob. So the overhead on Alice's side isn't all that much. On Bob's side, there's a more difficult task because he has to entangle the qubits, but Bob is supposed to have a universal quantum computer, so it's okay to put some of this overhead on him, or at least it seems okay to put this hassle of having to perform the entanglement on Bob's side. So this was implemented in an experiment. Stephanie did most of it under the supervision of Anton and Philip. Again, I was involved in this. So I should say Stephanie Bars, Anton Zeilinger, and Philip Walter. So the basic idea is that there is some source for the client that prepares the initial state with these random rotations applied, and they're transmitted to the server. I included this 3D graphic because I know Christian loves these. So the client is preparing the state that's sent to the server. The random rotations are already in place, so the server has to do random rotations and then measurement. And this is able to implement more or less the protocol that was on the previous slide. So you can run this and you can show that actually, yes, it hides a lot of information. You can use tomography to work out exactly how much was hidden in a particular run of the protocol. It turns out only about 0.18 bits of information were leaked, and that's basically due to imperfections in the way the states are prepared. But basically, this was used to demonstrate a 4-qubit computation, or rather, a computation on a 2x2 cluster state, or 4 qubits in a row. So it was used in several different ways, but basically each of them had 4 qubits in the resource state. Then, well, I guess prior to that experiment being performed, actually a much simpler scheme was proposed for hiding quantum computation using measurement-based computation. So this was proposed by Tomoyuki Murame and Keisuke Fuji, and the idea is actually very simple. So they say, well, maybe preparing single qubits isn't the easiest thing. Maybe it's easier to measure. Maybe it's easier to measure qubits than it is to prepare them. Now, I'm not sure if I agree with that, and it depends on the physical system, and there's a lot of caveats with that. But in this scenario, where you say actually the measurement is the easy thing, you can say, okay, let's let Alice do the measurement. So she's going to be able to rotate qubits and then measure them. And Bob is going to be the server. He's going to prepare the large entangled resource state necessary for arbitrary computation with some number of logical qubits and some maximum logical depth. So this can be just a regular cluster state, which is the main resource state that has been studied for this kind of thing. Well, not particularly in this context, but for encoding universal quantum computation. So the server just prepares the state and then feeds it 1 qubit at a time to the client. And the client just measures each qubit as it comes in, then decides the basis for the next measurement, and just waits for the next qubit to arrive from the server. And they proceed in this way until the entire resource state is measured. And I guess it's easy to see that this has to be blind, because nothing is ever sent from the client to the server. Right? The only thing they have to reveal at the start is the dimensions of this cluster state. And those dimensions are just basically the number of logical qubits they want to use and the total logical depth of the circuit. So this is a very nice way of formulating blind computation, and it's much simpler than our protocol. In certain circumstances, it has certain advantages for the other type of protocol, and indeed you're able to create hybrid protocols that kind of combine the two. I'll say something about that in a little bit. Well, actually, I'll say it here. So basically with these ones where Alice is preparing qubits and sending them to Bob, so the first protocol I told you about, or rather the second one, where Alice is preparing single qubit states and sending them to Bob, instead you can prepare the states by making a measurement on half of a bell pair sent from Bob to Alice. So you can kind of interchange between the two. So you can use measurements on Alice's side to implement the first protocol as well if you have Bob preparing and sending bell pairs. And in certain circumstances, that can be a better option, particularly if there's likely to be high loss over the communications channel. Because if Alice is always waiting on qubits that come from Bob that are part of the resource state, and some of them just get lost, some of the photons get lost in the communications channel, then she's lost physical qubits from her quantum computation. On the other hand, if you're doing this kind of thing, Bob's preparing bell pairs, sending it to Alice, Alice is making a random measurement on it, and then telling Bob it succeeded. In that case, when some of the photons are lost, some of the qubits are lost, it's no big deal. They're just never included in the computation. So once you go through this, you establish once you establish enough single qubits shared with Bob where the other half of the bell pair has been measured out, Alice can say, now with those qubits, entangle them into this state, and everything else proceeds by classical communication. So there's not really any danger of loss with the communications channel. So this also yields the idea that maybe instead what you could do is you could make Alice completely classical. So Alice doesn't have any quantum capability at all, but instead she talks to two different servers. And so what would happen then is that the two servers would share a bunch of bell pairs, and Alice would instruct one of them to randomly measure out his half. And when I say randomly measure out his half of the bell pairs, I don't mean that he's told, make random measurements. Rather, Alice generates random measurements and tells him to make those measurements. And then the first server sends the results to Alice. And so now Alice knows the states that have been prepared on the remote server. And so she has the same resource state that would have happened if she participated in the protocol where she was directly sending the states herself. The nice thing about this is that it makes Alice completely classical. There is, however, quite a big cost to pay for that. And the cost you pay is that the two servers can never talk to each other. If they ever talk to each other and compare notes after the computation has been run, they can reveal what happened. And that's the same with a lot of the multi-server protocols. There's essentially no multi-server protocol that I'm aware of that maintains blindness indefinitely, if the two servers can ever talk at any point in the future. So that's a bit of difficulty, because you can think, well, if I only cared about maintaining it for a certain amount of time, maybe I could use space-like separation or something like that, and I could hide it during the computation. But eventually they're going to be within each other's light cones, and you need to be able to deal with that. I mean, essentially, then you're going to lose blindness. So this gives some options. It gives us a way when we have a single quantum server, and the client has some minor quantum capability, maybe the ability to prepare single qubit states, or the ability to measure single qubit states. Then we know we can do blind quantum computation. We also know if you have multiple servers and a completely classical client, then you're able to do blind quantum computation again. Also, the easiest case is where you have a quantum client and you have multiple servers, because then you can take your pick of the protocols. Right? So in all these three cases, it's possible to do blind quantum computation. However, the case that will be really, really interesting, since IBM has started hooking up stuff to the internet, is whether it will be possible to have a single server and a completely classical client. So they don't have any ability to measure qubits, they don't have any ability to prepare qubits, they have no quantum powers at all, they just get to be able to do arithmetic on their classical computer. Say, well, in that case, is blind computation possible? And the answer is we don't know. There's been a bunch of papers about this, well, a few papers about this in recent years, suggesting that it's unlikely to be true, unlikely to be possible, that it would imply certain collapses in the polynomial hierarchy. So it seems unlikely. On the other hand, so there's some recent work from one of my students, Atul, and one of the postdocs in my group, Tommaso, along with Nick Menacucci, that gives some ways to actually hide non-trivial quantum computations that really cannot be distinguished after any amount of time. So you're hiding some set of quantum computations from the server. You're running one computation, and the server isn't able to distinguish it from some set of possible computations. Unfortunately, it's not the set of all possible computations on that number of qubits. Rather, it's some smaller set. And this is non-ideal, because it means we can't arbitrarily choose the type of computation we would like to be able to encode. And it means that if the server has some prior knowledge that really you're just going to implement Grover's algorithm or you're going to implement Shor's algorithm, and they're trying to decide between the two, it doesn't give you much security in that case. But nonetheless, it seems there's something you can do. And this relies on a very strange facet of measurement-based computation. So in measurement-based computation, what happens is you make a measurement on a single qubit, and then you need to decide how to make the next measurement. So when you try to make this next measurement, you need to account for the previous measurement results that have happened. And depending on the rule you use to make this correction, that's going to affect the computation. So here's an example. I've got I've got a single qubit. I've got 4 qubits entangled in this square graph state. So it's only a 4-qubit state, and I'm going to label the qubits 1, 2, 3, 4. And they will always be measured in the order 1, 2, 3, 4. Now, Alice is going to choose some measurement angles. Alpha for the first one, beta for the second one, gamma, delta. And she's going to tell Bob to measure in the first angle first. So she says to Bob, measure qubit 1. Bob measures qubit 1 in basis alpha, and he sends back some result to Alice. Now, Alice decides how to correct the next one based on which qubits she's choosing to be the input. So in this case, the inputs are marked by square qubits, and the outputs are marked by circular qubits with this little arrow on it. So in this case, the logical qubits are propagating from left to right, as I showed you on the earlier slide. But you can choose many ways to embed computations. In this case, you have an input here and an output here. And the qubit that's inputted here, it travels from 1 to 3 and then to 4, and it's outputted at 4. And the qubit that goes in at 2 also comes out at 2. So you can choose where you're going to place the input and output on this resource state under the restrictions of this fixed measurement order that you're always going to measure 1, 2, 3, 4 in that order. And each one of these is going to give you a different way of updating your measurement angles. So what's going to happen is Alice is going to ask Bob to implement this. So Bob implements the measurements one by one, sending the results to Alice, and Alice computes the next measurement. And there's a really nice feature of this, which is that if the measurement angles that Bob has been told after the corrections have been made to them are alpha, beta, gamma, delta, then depending on where the inputs are and the outputs are, this corresponds to completely different quantum circuits. And they cannot be distinguished at all. So there's simply not enough information in the protocol to tell Bob how to find the input, where it is, and or where to find the output, and depending on where that output is, that dictates what the computation was. And they're completely distinct. This circuit is not equivalent to this circuit under any circuit identities. They're just fundamentally different unitaries that are being applied. And it turns out, for this simple state, with 4, there were the 9 possibilities shown here. So you'll get the computation you actually implement will be indistinguishable from 8 other computations. But the particular 8 you get are somehow random. You don't really have control over which particular other 8 you're going to get. So there's some restrictions on that, but it does point to the fact that maybe it's possible to do some interesting things with a purely classical client, with purely classical communication, with a single server. And if you count the number of possibilities as you increase the number of qubits in the resource state, it grows exponentially. So the log of the number of possible computations on something like this goes up as something like 1.388 times the number of qubits in this. And it turns out that when you combine that with the number of possible choices for angles, in a particular run of the computation, there's simply not enough bits sent from Bob to Alice to identify the computation, no matter how he tries to encode it. Or rather, from Alice to Bob. There's just not enough information in what's sent from Alice to Bob. There's just not enough bits to be able to uniquely pick out one of these computations. So that kind of brings us towards the second thing I wanted to mention. So we're running a bit later than I thought, so I'll be a bit quick on this half. So the second application I wanted to talk about, the second class of protocols, relate to verifiable quantum computation. And you can say, what's the need for this, or what does it mean? The basic idea is that we have something that's claimed to be a quantum computer, and you have some user that wants to distinguish between whether it's performing the correct computation that they have specified, or whether it is basically some box full of magnets, or someone behaving maliciously and trying to convince them that it is indeed a quantum computer. Of course, I'm not ascribing these to any company or not. Okay, so There have been a number of protocols proposed for this based on blind quantum computation. There's several ways. The first idea was to use certain logical qubits within your computation as traps. So because the computation is hidden by blindness, you think, well, then the server doesn't know what operations are really being applied. So you could use some of the qubits prepared in certain known states that don't interact with the rest of the computation at all, and then you look at them at the end of the computation and you see have they been disturbed. And so originally we proposed doing this in kind of the first paper where we were proposing this single qubit preparation scheme. And unfortunately, we didn't prove it very well. And there's been subsequent work on that model by Broadbent, for example, who has quite a nice scheme for being able to hide quantum computation, essentially by having these trap states. Sometimes you're performing, sometimes you're acting on a logical qubit. Sometimes the server is acting on a logical qubit that's part of the computation. Sometimes it's a trap qubit. And at the end, you're just detecting whether the trap qubit has been disturbed or not. And from that, you argue that, well, if they deviated in any way from the prescribed protocol, they must be detected with some high probability. And hence, if they deviate, you're likely to catch them. We proposed another way, myself and Elham, that's based on measurement-based computation. So rather than taking a single line, the idea is to take just a single qubit within the resource state. And what you do is essentially you ensure by the states you pass the server to entangle that that qubit will not become entangled with the rest of the computation. And the way you do that is by preparing the neighboring states in either in either 0 or 1, so that the control phase gates don't entangle them with their neighboring qubits. And as a result, you're left with this isolated qubit that's not connected with the rest of the computation at all. And it's being rotated to some angle in the XY plane. And essentially, you're just asking Bob to measure it in that same angle. So you know what the result should be. You know to expect a 0 or a 1 from Bob. And if you don't get it, you say, well, you've been interfering with the computation. And the argument then goes that essentially, if Bob interferes with the computation in a way that's likely to change the outcome, then you're very, very likely to catch him. Now, that doesn't work when you've only a single trap. You need to use a lot of different traps. And if you want the chance to be exponentially small, then you need to use error correction, or you need to repeat the process many times. But still, it works very well. There's also another way proposed in this model where Alice is the one measuring qubits. So where the client is making measurements on qubits sent to the server. So in that case, it turns out that you can do tests based on measuring the stabilizers of the underlying graph state. So that was proposed by Hayashi and Morime in 2000. Well, I guess it came out in 2015. I think it was on the archive before that. So this is quite a nice model as well in the case where Alice is making measurements rather than preparing states and sending them to the server. So this kind of trap verification works in a fairly simple way. You just pick a random trap in the resource state. So in this case, the resource state is taken to wrap around a cylinder rather than being rectangular. And you prepare all of the neighbors on the same row as the trap and the row that it's connected to. You prepare all of them in the z basis, randomly 0 or 1. And that means that all of these CZs joining these don't actually perform an entangling operation at all. And the whole thing separates so that we have a single qubit prepared in the XY plane sitting on its own. And we have this brickwork resource state that's just completely separate from it. So we have a product state of this trap and of the resource state. So we do the computation on the resource state, and we use the trap to detect whether Bob has cheated on that measurement or not. And because that's randomly placed, you can detect whether or not Bob has cheated independent of where he chooses to cheat with some probability. And this can be amplified using various different techniques. Okay, and again, this was kind of experimentally implemented. in the 4-qubit setup. So you have 4 qubits arranged either in a linear configuration or in various ways that support 2 logical qubits. And you can place the trap in different places on this, different places in this state. Now, there were certain restrictions which meant that not all traps were possible. And there were some issues with that. So not all possible attacks could be protected against. But by randomly doing trap runs and randomly doing computation runs, it was possible to implement a verified computation. In this case, the computation was chosen just to basically be a bell test. And the reason, well, one of the reasons for that is the exact traps that we were able to do, given the limitations of that particular experimental setup. They detected all errors except for a particular correlated error that does not affect the outcome of the bell test, because you're always taking the parity of the outcomes. So the correlation in the error gets cancelled out when you take the parity in a bell test. So that's just an example of it being implemented again. And similar experiments have been done to implement, well, not for verification, but for the blind computation, to implement this kind of scheme where Alice is making measurements rather than doing preparation. And again, they're kind of with 4 photonic qubits. So that's kind of the state of the art experimentally. The demonstration of all of these things have been basically all with 4 photonic qubits. Okay, I should mention that Dorit Aronov, Michael Ben-Or, Elad Iban, and Urmila Mahadov have this protocol that uses quantum error correction as a way of ensuring verification. And it turns out that in their pursuit of verification, they also derived a blind computation protocol. It's just naturally blind. So originally this came out from Aronov, Ben-Or, and Iban in, 2010, and was on the archive in 2009. And basically the client could prepare, the client has some finite size quantum computer, which they use to encode logical qubits into some random quantum error correction code. It's a variant of the polynomial code, which they send to the server, and then the server implements logical operations between them. And it turns out that this can be used to verify the computation. So there was a subsequent paper going into this in a bit more detail, in which Urmila is included. That just came out last month, actually, so this is really quite new. And that can be used to verify that the computation has indeed been performed correctly, depending on whether or not the states remain in the code space of the error correction code. Okay, I want to finish off by basically mentioning the scenario of multiple servers again. But in this case, you care about verifying the computation, not about blindness. So a protocol was proposed, I guess many of you have seen this, from Ben Reichard, Volk Unger, and Umesh Vazirani, that uses 2 entangled computers, 2 entangled provers, to prove the result of a quantum computation. So this came out in 2013, so actually not that long ago at all in Nature, where the basic idea is that the 2 provers share a large number of bell pairs, and then you have a completely classical client or a completely classical verifier that is giving them instructions on what measurements to do. And based on the results they're getting back, they decide whether or not to accept the computation, or whether or not you've proven that a particular problem has a particular solution. I should also mention that this is very similar, this builds on a lot of work that had gone on long before this in the self-testing literature in relation to cryptography, but also in relation to self-testing quantum computers. Now, it wasn't taking, some of the previous work on self-testing quantum computation wasn't in this really extreme setting where you think the server might be cheating arbitrarily, but you make some extra assumptions on the ways in which it can cheat. But there was a lot of work on self-testing of quantum computations, and also particularly on self-testing quantum correlations. So Valeria's done a huge amount of work in this area, for example, where you're trying to verify that the correlations shared between two parties are equivalent up to some isometry to some idealized correlation based on measurement results. So based on that, based on ideas of self-testing of quantum correlations, Matt McCaig also proposed another scheme a year later. It came out fairly recently, but it's been on the archive for a long time. So he proposed a scheme that used essentially measurement-based computation again, combined with various self-testing ideas, to use, instead of using two provers, it used some polynomial number of provers to verify the result of a quantum computation. Since then, there's been a fair amount of movement. I'll kind of skip over this. There's been various different schemes proposed in order to be able to verify quantum computation using multiple servers. This is kind of nice in that it doesn't have to rely on the servers not being able to communicate beyond the end of the protocol. So in the blind case, if they could talk after the protocol, then the blindness is compromised. But if they talk after you verified that the computation was correct, well, it doesn't change your assessment that the computation was correct, right? You got the right answer. It doesn't matter that they now talk. So an alternate way of doing such tests is to encode the computation you want to perform as an instance of the local Hamiltonian problem. So it turns out there's a bunch of results that say that you can encode a quantum computation as the ground state of a particular Hamiltonian that has only local terms in it. So each term in the Hamiltonian acts on only some constant number of qubits. And if you do that, you can have the server prepare this ground state of this Hamiltonian that encodes the quantum computation, and you can use that essentially as a witness that a particular outcome to that computation is correct. So you ask the server, you can have the client choose their computation, then they ask the server, what's the outcome of this computation? And then with that outcome in mind, they say, well, also I want you to encode that as a ground state with that outcome, and you send it to me, and I'm going to test it. So what you can do is, well, the server could encode the ground state and send it to the client to test. The problem with that is just that the work the client would have to do is comparable to the entire computation. So you don't really gain much by that. However, it turns out that there are extremely efficient proofs for proofs that a particular Hamiltonian has a ground state below a certain energy that can be implemented with multiple provers. So the basic idea is that you have the server prepare this ground state, then they encode it into some quantum error correction code and give a share of that quantum error correction code to each of 4 or maybe 5 different servers. And then the client goes back and forth between those servers, asking them for only a small number of qubits from that witness state. And based on measurements of those either performed by the clients or performed on the servers themselves, the client is able to verify that, in fact, this witness state satisfies the properties that guarantee that this output was indeed a possible output of the circuit with high probability. So this gives another way of verifying quantum computation. It's kind of different from the others in that it's not blind at all. All of the other protocols that have been proposed for blind quantum computing have for verifiable quantum computing have kind of turned out to, by the way, also be blind. And so this is kind of a first instance where it's not. And an additional kind of interesting feature of it is that it takes place after the protocol has been performed. After the computation has been performed. So you ask the server to perform the computation and prepare the witness state, and then you're going to test it later. You don't have to do it while the computation is going on. Pretty much all of the other work prior to this is based on the idea of testing gates as they happen, or testing various elements of the computation as they happen. So this kind of gives an alternate option. Now, if you kind of look at these, it gives you a kind of arms race for this 2-server setting, or this multi-server setting. And I'm going to combine these. I'm not going to care very much about the number of servers you require. Just there's some number of servers, they don't have to communicate. So this I'll measure them in a very scientific way, compared to the size of the universe, the sun, number of atoms in the Earth, number of photons in a 100-watt light bulb per second, and so on. So the first really breakthrough result from Reichardt, Unger, and Vazirani, if we want to verify a two-gate computation, well, that comes in at 10 to the 2,466, which is significantly higher than the number of particles in the universe. So this is the number of bell pairs you'd need. And that's, I mean, it's a really phenomenal result, and I'm not knocking it. But it's impractical if we want to actually try to use it to verify quantum computation. So if you look at McCaig's scheme, it turns out it does much better. It does much, much better than the Reichardt, Unger, and Vazirani scheme, coming in at only 10 to the 52, which isn't too bad. Like compared to the, this is substantially less than the size of the universe, the number of particles in the universe. So you can, in principle, there can, in principle, be enough bell pairs, within our observable universe, even within our solar system, to be able to implement this. But still, we would really like to get further down. So the first result came out in 2012. McCaig's result came out in 2013. Then a couple of different groups start looking at, is there ways to improve this, and is there ways to combine these results with the other type of verification where you have Alice doing quantum operations. Maybe you can use this measurements on bell pairs as a way of preparing states, like I mentioned before. Maybe you could use some self-testing from the Reichardt, Unger, and Vazirani scheme, or the McCaig scheme, or one of the cryptographic self-testing schemes, in order to reduce the overhead. Because in the other model, where Alice can do quantum operations, the overhead's really low. I mean, it's sublinear, so it's really low. So there were some attempts at this. Elham and some of her group tried to use our trap-based verification scheme with combining it with the RUV result, and they got something like 10 to the 616. So they got a reduction of a fourth root, I think, from the RUV scheme. So that's significantly lowered the overhead of that. It should be said that these are both with two provers, whereas these lower ones are with much more than two provers, some polynomial number of provers. Okay, so we used similar self-testing techniques that McCaig had been using and Valeria has been using and so on in a number of different works, to use that as a way of checking that you can prepare a particular input state, a particular single qubit quantum state for the server, and then using our trap-based scheme. And if you do that, it comes in, it's not too bad, actually. It's, a light bulb shines out more photons than it in a second, mostly. Although it's still kind of impractical because it's kind of hard to get 10 to the 14 bell pairs. You would need a really bright laser and a really big crystal, and you'd need to run for a very long time, and it's basically impractical. Subsequently, the next year, Masahito and Mikhail came out with this result. I may be being unfair to them. So I've written it in as 10 to the 14, but actually that's just because I copied the number from our result. And the reason I did that is because theirs has the exact same scaling. But I'm not sure if the multiplicative constant in front of it is the same. So both of these protocols scale with the number of qubits to the power of 4 times the log of that number. So n to the 4 log 4. Sorry, n to the 4 log n. So I'm kind of guessing that their number is similar, but it may be that there is improvements in the prefactor, so they may be doing better than us here. There's also a very nice result that came out just towards the end of last year from Natarajan and Vidic. And I don't know how it scales, but I think it's good. So it seems quite hard to work out exactly what the scaling is, or at least to work out what the number would be for two gates, or at least harder than I was prepared to put in preparing my slides for this talk. But it looks low because they can verify a polynomial number of bell pairs essentially with a constant amount of effort. And that seems like it really has the promise of significantly lowering this. So that's why I'm putting it on yellow or green. I'm not really sure. I'm not really sure whether it brings it to a really, truly practical level or not. But certainly it's probably worth looking into. Okay, and that's basically it from me. I'm sorry I've kind of run over time. There's a whole load of areas in secure computation that I haven't touched. And if I tried to include all of them, some of the original results were in secure multi-party computation. And then in recent years, there's been computing on encrypted data, which is kind of related to blind computation, but where you don't try to keep the secret. You don't try to keep the computation secret, just the input. There's quantum versions of homomorphic encryption that are starting to be discovered. There's computing on shared secrets. There's self-testing. There's a huge number of areas that are all kind of in this domain of secure quantum computation. But if I talked about them, I would be here, until next week or something. Okay, so let me conclude by saying the really big open problem in this, at least from my perspective in this field, which is, can a purely classical verifier check that a single quantum computer is producing correct results? So you have a quantum computer in front of you. You want to know the answer to some problem that's within BQP. Can you do some test with that computer to ensure that you get the right answer if you don't trust that computer at all? So that can be phrased in CS terms and say, is the language BQP equal to IP BQP, where these are interactive proofs, where the power of the prover is restricted to BQP. And maybe as a precursor problem, we can say, is blind computation possible with a purely classical client on a single server? And the reason I bring this up is because almost all of the verification schemes we've seen are either intentionally blind or get blindness as some unintended consequence. However, there's some very recent results from last month from Aronson and various people in Elham's group arguing that such a result would imply a collapse in the polynomial hierarchy, and so is unlikely. So you might say, well, maybe this is reason not to look for it. If this is going to imply complexity results, well, we know they're hard. Why even look? Well, maybe we should look because maybe it's a different way of tackling complexity problems. Maybe it is. Okay, so with that, let me finish, and thank you very much for your time, and more time than I think you intended to give.
Thank you, Joe. I think it was anyway very interesting, and maybe there's some questions. We can take some questions here. Is there anyone? Yes, please.
So with these trap schemes for verification, how do you tell the difference between malice and incompetence?
You can't.
So if there's noise in his computer, then
they're not checking that Bob is cheating. They're checking that the result is correct.
Right.
So the reasonable use case for them is to check that the result you get is correct, not how it went wrong. So this raises some issues of how you could make some of these schemes fault tolerant or not, or whether that's possible, because you need to strike some kind of trade-off where you're accepting the fact that a certain amount of environmental noise happens, but you want to ensure that it is sufficiently uncorrelated and sufficiently weak that some inbuilt fault tolerant scheme will be able to take care of it.
Anyone else? Not maybe. Joe has forgotten to mention, it's written here that he has written sort of a review paper on this thing. So if someone wants to go through the slides, again, maybe more detail, you can also read this paper. And we can thank him for a nice talk.
Thanks very much.